are examples of corrosion from RAF aircraft. As can be seen, unless it's detected at an early stage, it can become quite severe. In fact, corrosion is a serious problem in many of the aircraft now in use, and putting it right needs many thousands of man-hours, most of it during major servicing. Total costs run into tens of millions of pounds each year. But before we see how corrosion can be rectified, or better still, prevented, we need to understand more about its causes. We'll begin with one of the most serious forms. Aircraft construction involves the use of various different metals, steel, aluminium and magnesium alloys, for instance, as well as materials such as carbon fiber composites. Each of these has a characteristic electrochemical potential. This is a measure of how readily that metal will replace other metals in solution. For instance, if we put a small piece of steel and one of aluminium in this water, and we connect them to a galvanometer, we can see that a small current flows between them. This is because the electrochemical potential of the steel is higher than that of the aluminium. The consequence is that the material with the lower potential, the aluminium, will be slowly eaten away. This is known as galvanic corrosion, and the bigger the difference in potential between the metals, the more rapid the corrosion. Magnesium, for example, has a lower potential than aluminium, so in contact with steel, it corrodes even faster than does aluminium. Another factor which aggravates the problem is the presence of salt or other impurities in the water. This lowers the resistance of the electrolytic cell that's been created, and as we can see, the current flowing is much greater, so the metal will be corroded more rapidly. And we're not just talking about something that happens in the laboratory. Think about a steel fastener in contact with an aluminium panel. Put them in a wet and possibly salty environment, corrosion is a certainty. In practice, such processes usually occur quite slowly during the normal life of an aircraft, and a great deal can be done at the design stage to prevent them happening at all. Good design will help to prevent the onset of corrosion, both by considering the susceptibility to corrosion of the materials chosen and by designing in such a way that the circumstances which promote corrosion are avoided. Let's consider the materials first. Metals which we know are prone to corrosion, magnesium alloys for instance, can only be used in exceptional circumstances, where weight saving is especially important perhaps. In this case, they must be carefully protected, well ventilated, and easily accessible for inspection. Such metals are not allowed for components where the protection is likely to be damaged during operation. Carbon fiber, on the other hand, has a high electrochemical potential, similar to that of gold, so its insulation from most other metals is critical. The susceptibilities of the different materials are well known, and there are clearly defined standards and techniques for building aircraft, as well as for dealing with corrosion prevention measures. For instance, the corrosion resistance of metals can be critically affected by the heat treatment they receive, as this affects the microstructure of the metal. New manufacturing techniques may also have an impact on design. This is superplastic formed titanium. Titanium is highly corrosion resistant, and the combination of this forming technique with the process of diffusion bonding reduces the number of fasteners needed, so cutting down the number of potential sites for galvanic corrosion. Now, the design considerations. The aim is to prevent moisture and other pollutants from finding their way into the structure. Any liquids that do get in must be able to drain away easily, so cockpit and other drainage systems are provided. Crevices which trap and hold water or other fluids must be avoided. Even so, some areas will still get wet or dirty. This could be due to water vapour condensing inside the aircraft or to the actual spillage of liquids in galley and toilet areas. So thorough protection, inside and out, is vital. Manufacturers also take a lot of trouble to ensure that components remain corrosion-free prior to assembly. Monitoring cutting fluids to ensure they don't affect the metal. Handling components carefully to avoid surface damage and abrasion. All components and sub-assemblies are pre-treated and primed all over, not just on outer surfaces. The primer contains a corrosion inhibitor, and the finish protects the primer. In order to ensure there is no contact between metals and to prevent fluids getting in, wet jointing compounds are used during assembly. All wet assembly materials are corrosion inhibited. Crevices and depressions must be filled with sealant. Other treatments used include cadmium and zinc plating and zinc or aluminium spraying. These either reduce the galvanic potential between the metals in contact or provide a sacrificial coating which is eaten away in preference to the base metal. However, despite good design, use of suitable materials and effective methods of protection, corrosion will inevitably occur due to a variety of operational factors. Indeed, as some aircraft have been kept in service for far longer than envisaged when they first appeared, the problems are sometimes severe, as the degree of corrosion damage is calendar dependent. The environment itself can be aggressive, and aircraft stationed by the sea spend all their time bathed in a salt-laden atmosphere. This problem becomes much more severe when they fly over the sea at low level. Helicopters often work in similar conditions and can suffer from salty water being brought inside the machine. Corrosive liquids may be carried as part of a cargo, mercury or battery fluids, for example. Dust and abrasion can severely damage the protective finish and allow corrosion to get a grip. Of course, these effects are unavoidable if the aircraft are to fulfill their operational role, but there are others which can be avoided. Equipment or components being removed and scratching the surface. Failure to use protective matting on a wing surface. Snow removal being carried out harshly. Incorrect footwear being worn. The area around fasteners getting scratched. Careless stacking of panels. All trivial incidents on their own, but happening regularly over a period of months, the cumulative effect is serious. corrosion is being offered a chance to take hold, a chance that's always accepted. So what form does corrosion take in practice in RAF aircraft? What should we be looking out for? One of the commonest forms is surface corrosion, a general etching away of any exposed areas of bare metal. Pitting corrosion is more localized and occurs particularly where strongly corrosive agents are found, places such as battery compartments, toilet and galley areas. Any crevices that trap liquid are also very prone to corrosion, as the lower oxygen content of the trapped water gives rise to an increasingly acidic galvanic cell. We've already considered the problem of dissimilar metals in contact. The effect is commonly seen around fastener holes. Intergranular corrosion is less easy to detect. There may be little or no sign of it on the surface, and the attack is concentrated on grain boundaries within the metal. The corrosion products then force the grains apart, and a great deal of metal can be lost from a relatively small amount of corrosion. In extreme cases, this may lead to exfoliation, a layering and flaking effect. Fretting corrosion is due to small movements between two load-bearing surfaces. These break down the protective treatment, leading to corrosion, and the corrosion products then act as an abrasive. Microbiological corrosion can occur in fuel tanks, although it's normally inhibited by the use of a fuel additive and by the use of chromate bags in the fuel tank sump. Galley and toilet areas may also suffer from this type of corrosion. It's caused by the growth of fungi or bacteria. All these types of corrosion occur in our aircraft and present a threat to the structure, depending on where they occur, of course. And it's not only the airframe which is affected. Engines, undercarriages, electronic components, all are liable to suffer. The threat is even worse, however, when the corrosion is associated with either stress or fatigue. Some alloys prone to exfoliation corrosion, when used in certain components, such as this section of Canberra, will also be liable to stress corrosion cracking. It occurs particularly when the metal is subject to periods of tensile stress. Even minor damage to the surface protection may lead to cracking, despite little corrosion being evident. Another contributing factor may be built-in stresses caused by manufacturing processes, such as the pressing in of interference-fit bushes or bearings, or by misalignments during assembly. Even items held in store which contain built-in stresses and have been inadequately protected may be issued with cracks in. When it does occur, stress corrosion cracking may proceed very rapidly, posing a serious threat to the integrity of the affected structure. Similarly, fatigue and corrosion together act more drastically than one would predict from simply adding their separate effects. The combination of corrosion with either stress or fatigue can lead very quickly to structural failure.
Much of the corrosion that does occur is not really identified or rectified until the aircraft returns to its major servicing unit. By this stage, the problem can be severe. Corrosion on this scale takes a considerable time to deal with.
Specialist NDT inspection may be needed to check the extent of corrosion. This may involve use of the ALCO probe, for example. Rectification is usually accomplished by either cutting away the affected area or by abrasive blasting with a stream of fine alumina grit. This scours away the corrosion products, leaving a clean, dry metal surface. Chemical treatment is then required, but it's necessary to ensure that all the reagents have been removed afterwards. These methods can be very effective, provided the corrosion is not too deep. In some parts of the airframe, however, removal of metal could affect the strength of the structure, so new sections may need to be fitted. After rectification, the surfaces must be re-protected using primers and paints. These need to be correctly applied and given adequate curing times. Details are given in the special finish paint repair schemes prepared for the RAF.
The fact that we need to spend all this time at the major servicing unit rectifying corrosion is unfortunately proof that preventive measures have failed. And it is prevention which needs to be at the core of any effective program for corrosion control. So what can be done at an earlier stage to reinforce the protection schemes and prevent damage becoming so severe, to reduce the time and money spent on rectification? More time devoted to prevention at first and second line level will help a great deal. Thorough washing and cleaning will remove corrosive agents. Frequent visual inspection is important. The skilled tradesman will know where the most likely areas are and what the signs will be. The paintwork around scratches and abrasions should be touched up at the first sign of damage. A few minutes now could save hours of someone else's time later. Additional medium-term protection can be obtained by using PX32. This is a solvent-based wax protective, and it can be applied either by brush or by high-pressure spray. It dries within 24 hours to give a tack-free dry coating. Since it's transparent, surface deterioration or cracks can still be seen. For areas prone to damage, such as undercarriage bays and legs, PX32 is not satisfactory, as it would need to be reapplied frequently. PX24 should be used instead to displace moisture and retard corrosive action, although it gives only temporary protection. Both materials may be used only when specified in servicing schedules.
Cracking would appear as cracking. Exfoliation corrosion would appear as like paint bubbling or paint.
Remember, above all, that corrosion is a specialist subject and requires expert knowledge. Each unit will have a corrosion control specialist who has undergone training at RAF Halton. He will also have a copy of the corrosion manual, which is a comprehensive reference book on the subject. He will be available to advise on and check the effectiveness of the corrosion control measures being used. If you have any doubts or questions as to how to deal with corrosion at first line level, then ask for his advice. Effective prevention, however, needs the participation of all who work on the aircraft. Everybody needs to be aware of the problems. Do you know where to look for corrosion on the aircraft you deal with? Do you know what the signs are? If you do find it, do you know what action to take? Are you remembering to use preventive measures at all times and avoiding careless damage to protection schemes? Your answers to these questions will have a major influence on whether the RAF can hold maintenance costs down and keep corrosion at bay.